All right, everybody, welcome to chapter 12, not chapter 11. I apologize for the mix up. Chapter 12 is going to cover some information on solutions. And so our first section covers the initial info, things like what are solutions defined as from a chemistry standpoint, and then some other descripting terms that we're going to go through. So just to start off, very basic, obviously one of our first definitions is going to be this idea of solution. So a solution is considered something that is a mixture of two or more substances in a phase, one single phase. So for instance, two gases mixing together is a solution, two liquids mixing together is a solution, two solids mixing together is a solution, commonly referred to typically as an alloy, and things of that nature. Another thing we have to discuss is this idea of solubility. So if we have a substance, a solid substance typically, that is able to be dissolved into another substance, we call that interaction soluble. So what that means is something like sugar and water. We know that sugar is described as soluble in water. Now, if water was replaced with something like hexane, we would have to do some tests to see if it was soluble in hexane, but if it was, then we would say it's soluble in hexane. So we can say anything is soluble in anything else if and only if it dissolves and you can no longer distinguish the particles as individual particles. So for instance, when we drop sugar in water, eventually all of the sugar disappears as long as we haven't put too much in, and that becomes a sugar solution, if you will. From there, then we have to describe parts of our solution. Now, the thing in which we dissolve something, or the thing in which we is present in the larger part, is typically referred to as the solvent, and the thing being dissolved in the solvent is called a solute. So for instance, the sugar and water situation on the previous slide, as long as the sugar is present in less of an amount as the water, then we call the sugar the solute and the water the solvent. Now, our solutions can be in any phase. Our gases, liquids, and solids are obviously our phases that we're going to talk about here. An example of two solids that are mixed together to create a solution are alloys. So things like brass, sterling silver, 14 karat gold, all of those are good examples of alloys that exist as a combination of two solids. So here we see two solutions. We see ethanol and water, which is two liquids that are joined together, and then we see silver and gold. An alloy of silver and gold is referred to as 14 karat gold, or some kind of karat gold. The karat implies how much of it is actually gold, the rest of it being another metal. From there, we discuss suspensions. So we've got our first one is a solution, and we'll talk about what identifies a solution as a solution. Our next one's going to be what we call a suspension. So in a suspension, our particles are really, really big, and suspensions are known for being the types of solutions that settle out. So eventually our parts kind of join themselves back into their original phases, and they kind of settle into many different layers. So think like your homemade Italian dressings or salad dressings that have oil and water or oil and vinegar. When you let it settle for a while, they kind of become the oil phase and the vinegar phase, and that is just an example of a suspension. Now, if we wanted them to mix evenly, one of the ways to do that is actually to get our particles to be smaller. So suspensions are pretty identifiable by the size of the particles and that settling out thing that we just talked about. Colloids are going to be another type of solution or a type of mixture. Our colloids have smaller particles than our suspensions, but still they have particles that you can still see or that cause some kind of an issue inside of the solvent itself. So in this case, we have a dispersed phase and the dispersing medium. So the medium is just like we said, solvent. It's going to be the thing present in the larger amount, and the phase that gets dispersed throughout is known as the dispersed phase, so the thing we add to it. Colloids are known to be different from suspensions because when you mix them, they tend to stay mixed. So our examples here are things like mayonnaise, and if we make it correctly, an emulsion. So emulsion being different than a suspension. Emulsion meaning that the things are mixed so well and the particles are small enough that they stay mixed, they don't settle out. And from there, we can identify a colloid by what we call the Tyndall effect. So our colloids look very similar to our homogeneous solutions that we talked about first in this section, in that you can see that they look pretty evenly dispersed. However, Colloids tend to scatter light particles. So if you take your flashlight and you shine it through a clear glass of water, and then you take your flashlight and you shine it through what we would call a colloidal suspension of some kind, a colloid would scatter the light. So the light beams would not transfer straight through that suspension. They'd get kind of bounced back at you, or they'd get bounced off to the side. And a good example here is like at night when you're driving, if you turn on your high beams and it's foggy, you know that the light doesn't penetrate the fog, it gets pushed right back. So fog is a good example of a colloid or a colloid of some kind. The Tyndall effect is a really big, useful technique that we use to differentiate a solution from a colloid, not to identify a suspension from a colloid, just a solution in a colloid. Okay, so some examples of some colloidal suspensions. On the left, you see a colloid, and you can't see really the beam of light going through the colloid on the left. But with a colloidal suspension on the right, if we try to shine a beam of light, what we're actually going to see is that light being scattered and kind of bounced around and then kind of bounced outward. That's why we see the beam of light we do. And then from there, we have this good example of how to identify each individual one. So the only homogeneous type of solution that we know of is referred to as a solution, meaning perfectly mixed. You can't distinguish one particle from another. It doesn't separate. You can't separate the two parts by filtering them. It doesn't scatter light. Okay, so our colloids are going to have a few things in common. So we're going to have slightly larger particles. They don't separate, just like solutions. You can't separate them by putting them through a gravity filtration system, but they do scatter light, and they are considered heterogeneous. And sometimes you can even see the particles if they are large enough. And then finally, we have our suspensions, which have very little in common with our solutions, but some things in common with our colloids. Again, they are also heterogeneous like our colloids are, but their particle size tends to be very large. And because they're so large, this allows those particles to settle out. So it has that, that is what one of the things that distinguishes a suspension from a colloid or a solution. Suspensions can also be separated by filtration. So if I wanted to, I could let the two layers separate themselves by letting them sit for a while, and then I can remove the top layer and I can put that off somewhere else. And the very last thing is that in the Tyndall effect, the Tyndall effect doesn't really work here. They might scatter light. They're definitely not going to be transparent like colloids can be, but that's not going to be a good way to actually distinguish a suspension from a colloid. So just kind of remember, the Tyndall effect does not distinguish these two. It only distinguishes these two because both of these can be transparent, not clear, transparent. All right, that brings us to our first lecture question in chapter 12. If you need help, you can go back to that chart. That is what I would use to help you describe this particular question. And when you are done, you can go ahead and you can go forward. All right, next thing we're going to talk about, still in section 1, is this idea of an electrolyte versus a non-electrolyte. So very simple. When you put anything in a solution, so again, we're adding a solute to a solvent to create a solution. The solute that you add, if it dissolves into two parts that are ions, so a positive and a negative ion, aka an ionic compound like salt, when you dissolve that into the medium of water, so the solvent of water, we see that those positive and negative ions can actually conduct electricity, and that's what defines that solution as an electrolyte solution. And you've heard this term electrolyte before, it's not the first time, but what we're doing is we're actually making it so an electric current could pass through. So if you've ever seen anything that's like a saltwater clock or a saltwater powered anything, what they're actually doing is they're running an electrical current through it, and they're just saying, okay, look, this conducts electricity. Pretty cool. A non-electrolyte is going to be something that when it dissolves does not dissolve into ions. So for instance, sugar. When we dissolve sugar into our water, it does not dissolve into positive and negative ions, so it cannot do what we're talking about in terms of conducting electricity. Brings us to our second question for this particular section, and this is the last question in this section, but we still have a little bit more to cover. So in this particular section, I want you to talk about the difference between an electrolyte and a non-electrolyte. From there, we're going to talk about just like what we're talking about. So for instance, if we look at strong electrolytes, we have a really strong powered battery light. If we look at non-electrolytes, we see no power is conducted through those leads. If we look at different weaker acid versus strong acid, so HCl is a strong acid and acetic acid, which is vinegar, is a weak acid. If you stuck 2 leads into a beaker of vinegar, you would actually see that the beaker would conduct electricity. Same thing with salt water. And that's the end of section 1. Next section, we talk about a couple of different things. First thing we're going to talk about are some of the factors that affect how quickly something dissolves. So first one's going to be the surface area. So if we're talking about how to dissolve something quickly, we can increase surface area of a solute by making sure that whatever we add is in the smallest form possible. So for instance, if we take our tablet of what was it that we dissolved in the balloon? Sorry, I'm having a brain fart. If we take that tablet of Alka-Seltzer and we dissolve and we crush it, what we're doing is we're increasing the contact of each particle with the actual solvent when it hits the solvent. And this is done by the fact that when we pounded it into a pulp, what we got out was this powder. Each of those individual pieces of the powder has full surface area with the solvent that it's going to come into contact with. So in our case, it was water. And when it does that reaction quicker. So if we had just tried to put the whole tablet in there, it would have taken a lot longer to get the reaction to occur. So we increase the rate of the dissolving or the process that we're trying to do by increasing the amount of surface area each particle has with the solvent itself. The next one is going to be stirring or shaking, and we've seen this happen too. So if we stir or shake a solution, we'll actually get the reaction to dissolve quicker, or we'll get the thing to dissolve quicker, or the reaction to occur faster by stirring or shaking. The next thing that we can do is we can increase the temperature. So if we increase the temperature of the solvent itself, and then we try to add solute particles, then we see that it actually takes less time for those solute particles to dissolve. This has to do with energy and how quickly the particles are moving. The faster they're moving, the more likely they are to bounce and hit each other. Frequency of collisions means higher interactions, and higher interactions means higher rate of dissolving. Next thing we can talk about is this idea of a solubility. So how soluble is a substance in a solvent? And one of the ways we can talk about this is we can give a measurement of how much of a solute in grams could dissolve in, say, 100 grams of water. Every substance is going to be different. For sugar, it's going to be really high. For something that is less soluble than sugar, that value is going to be low. And there are a lot of different ways to determine this, but we can get these values of solubility that say things like, this much of the salt will dissolve in 100 grams of water. This much acetic acid will dissolve in 100 grams of water, and so on and so forth. Okay, the point at which we reach the limit. So if we say 150 grams, if we say 15 grams of salt will dissolve in 100 grams of water, that 15 grams, once we hit it, is the limit. That limit has a defined title. That limit is typically referred to, I will tell you here in a second, but for now, what I want you to do is I want you to tell me the ways in which you can increase the rate at which a solution is made. So you can go back and you can look at that. You can go forward when you're done. Okay? So back to what we were talking about. We're talking about the rate at which these things are going to occur and how solubility is going to be involved. So here we have 2 solutions. We've got toluene and lithium chloride on the bottom, and we've got water and lithium chloride. So lithium chloride is a salt, and water is our solvent in the first diagram, and toluene is our solvent in the second one, with lithium chloride being our salt in the second one as well. So our toluene is our solvent, and our lithium chloride is our solute in both solutions. All right, so in the top diagram, we know that salts tend to dissolve when they hit water, and we're going to talk about why. And down at the bottom, we're seeing that the lithium chloride salt is not dissolving when it's in this toluene. Now, the difference between the 2 solvents, the water and the toluene. Water is a polar substance. We talked about this in chapter 10 that we just finished. Toluene is a nonpolar substance. This idea of polar versus nonpolar comes into play when we're trying to dissolve an ionic compound. Ionic compounds like lithium chloride really love to dissolve in polar substances because polar substances have the ability to put their negative side towards a positive atom and their positive sides towards a negative atom. Toluene, which doesn't have a negative or a positive side because it's a nonpolar molecule, does not have the ability to arrange itself to attract the negative and the positive sides of our salt if our salt was able to dissolve. So that being said, looking just a little bit closer, what we're going to see is when we try to even put toluene in water, the two do not mix because again, nonpolar, polar. These things like to arrange themselves so that they have a side they're attracted to. These things don't like to interact with anybody. They don't interact with themselves. They don't really interact with anything polar. They will interact with other non-polar substances, but this idea of these two things not mixing is referred to as insoluble. This idea of these things mixing well is referred to as soluble. Okay, so when we talk about solubility, we just want to think about when we add a solute to a solvent. So what's going to happen if the things are in the same polarity? So if we have a polar thing with a polar thing, they are going to interact. If the things are polar and ionic, so the salt plus the water, polar and ionic are going to interact just like polar and polar. And the reason being that this has to do with at the molecular level, that the things that are at the surface of the solid that's being added to our solvent are going to interact with the solvent first, and then they're going to keep doing that over and over and over again. So as they pull something away at the surface, new particles are at the surface below it, so those are going to get grabbed and pulled away, and so on and so forth. And this is going to continue until we get to the limit that we talked about just recently, that limit of how much can actually dissolve in one of the amounts of solvent that we talk about. This creates what we call a solution equilibrium. So when we hit that limit, we have no more solid going into water and no more water that's actually interacting with solid. Now, this equilibrium is what we call the state at which the rate of dissolution equals the rate of crystallization. So the rate at which it takes, so how quickly it happens that something is being dissolved at the surface of our solid, is the exact same rate at which we're forming new solid particles at the surface of something else. So equilibrium, remember, it's dynamic. That's something we talked about in chapter 10. Just because we say something has hit equilibrium does not mean that thing stops reacting. It just means that it's happening at the same exact rate as something else, okay? Moving on, we'll talk about saturated versus unsaturated. So this is where I was going before. When we reach that limit, we are at what we call a saturated solution. So when we have put the amount of solute we can into a solvent, we reach this limit of saturation. So a saturated solution is considered one that has as much as it possibly can dissolved in the amount that we started with. So for instance, if we have our 100 grams of water, we get 15 grams dissolved. Any more than 15 grams and the solid won't dissolve. It'll just kind of sit in the solution. If you want to do this at home, please do. Try to make yourself some Kool-Aid or just add a bunch of sugar to water. Tell your mom you're going to waste sugar and water and hopefully she'll be okay with it. Put a full glass, say 8 ounces of water together, and then start adding spoons of sugar until, add a spoon of sugar, stir it, add a spoon of sugar, stir it, etc., etc. Keep doing that. And when you get to the point where it doesn't dissolve anymore, you have gone past saturation. So if you remove whatever's at the bottom of the glass and you just take the liquid out, that is a saturated solution at the temperature your water is at. Now, if you don't add enough sugar to your water, you are creating an unsaturated solution. So you haven't quite added enough. You could dissolve more. That's what an unsaturated solution is. The very last one that we want to talk about is what we call a supersaturated solution. But just to kind of give you an example of how this would look in a graph form. Anytime before you reach the maximum amount the water can actually dissolve, you are unsaturated. Once you reach the maximum amount, you're saturated plus extra. Okay? And remember, I told you that our solubilities are typically given in terms of grams of the solute over grams of the water. A supersaturated solution is one where you mess with temperature first. So, for instance, you heat your water first, say almost to boiling, and then you start adding your solution. Well, if you keep adding and then you start adding your sugar. If you keep adding that sugar, keep adding the sugar, keep adding the sugar, you just keep adding it, you're going to actually be able to dissolve more than you would if it were at room temperature. And eventually you won't be able to dissolve anymore. Very common. And what we would see is we'd have a little bit extra laying at the bottom. If we then turned off the heat, removed it, didn't touch it, we would see a crystal form. We would start seeing these crystals form. If you've never done it before, I highly recommend you take that sugar water that you were messing with and you start trying to make rock candy, because this is how rock candy is made. We put a little bit of dye in there, and then maybe you toss in like some lemon or some orange essences or something if you want it to have a flavor, and you let it sit. You hang like a string down in it. You let it sit overnight and you come back and you have these beautiful crystals of rock candy. That rock candy is a super saturated solution that formed crystals. Those crystals come from a super saturated solution. Okay? I will send a video out for you to look at or for you to watch, and it'll just be like a how to make rock candy. What that is just the science behind rock candy is super saturated solutions. And that brings us to our next question of this lecture, which is to describe each of the three types of solutions we just discussed. I want you to give me a description of the saturated and unsaturated and the super saturated form of the solution. Okay, when you're done, you can go ahead and you can move on. Next one's going to be our solubility values. So remember we said that we could report it as an amount of grams per 100 grams of water. This 100 grams of water on the bottom is a very established value. A lot of times if you look up the solubility of blank anything, not just sugar, you look up the solubility of salt, or you look up the solubility of lithium chloride, or you look up the solubility of XYZ chemical, you'll find it in terms of 100 grams of water. Now, they are sometimes very big. They are sometimes very small. Again, they have been determined experimentally already. There aren't very many things out there that don't already have a reported solubility value. This is kind of like any other constant. You'd have to be given this information if you were expected to do a problem with it. That being said, we have some other things that we want to talk about. So whether or not things are soluble in other things is something we can use charts to determine. So for instance, if we look at this chart, and there's two of them, the first one we're going to look at are some common ions. If we look at this chart, it says that compounds containing the things on the left are soluble in water unless they contain a certain ion on the right. So for instance, all compounds containing NH4, so ammonium, are soluble in water. No exceptions, all of them. But if we look down at, say, chloride, we say all compounds containing a chloride ion are soluble in water, except if it's attached to silver, mercury, or lead. So in other words, if we had AgCl or PbCl2, those two would not be soluble in water, meaning when you tried to dump it in water, it wouldn't dissolve, it wouldn't disappear, it would just kind of settle at the bottom. For nitrate, all nitrates, anything containing NO3- are soluble in water. But if they contain a certain ion, so there are no exceptions here, it would make it insoluble. So all nitrates are soluble, no exceptions, every single one. All sulfates are soluble, except if they are attached to calcium, barium, lead, strontium, or mercury. So that means calcium sulfate, not soluble in water. Learn how to read these charts. I'm going to ask you questions over these charts moving forward. Would you always have access to this chart? Absolutely. The second chart has it kind of flipped. So on the left, it says these compounds are insoluble in water. So oxides, just O. If they're attached to something, then they would be soluble. So for instance, oxide, all of them are insoluble in water. Every single one. There is no exception. But phosphates, all are insoluble in water, so they don't dissolve unless you have, say, potassium phosphate. Potassium phosphate is soluble in water because it is attached to the potassium ion, and it is one of the exceptions to the insoluble rule. So this one says everything is soluble except on the right, and this one says everything is insoluble except on the right. Okay? Like I said, make sure you teach yourself how to read that. I will have questions for you over these sections, and it will involve identifying, is this soluble in water? Is this soluble in water? Is this soluble in water? And so on and so forth and so on and so forth. Okay, so next thing we want to talk about is solubility and how to just know if something is soluble or not. This is something we can predict based on polarity. So this says polarity or non-polarity of molecules. That's what we're really going to focus on. Type of bonding is also going to matter because we know ionic substances tend to dissolve in polar substances, but polarity and non-polarity is going to mean a lot here. Remember, a very, very polar molecule is called an ionic molecule. So polarity and non-polarity are going to be what we use to determine if something is soluble or not, aside from the chart we saw on the previous slides. So the idea of like dissolves like means it's very like random saying, but what it means is if you have a polar solute, it will dissolve in a polar solvent. If you have a non-polar solute, it will dissolve in a non-polar solvent. So there is a very good way to identify it. Well, it's water. Is what it's trying to dissolve polar? Then yeah, it's definitely going to dissolve. Is what it's trying to dissolve non-polar? Then it's probably not going to dissolve because water's polar and that thing is non-polar. If they're the same type of polarity, they will probably dissolve in each other. Okay, dissolving them in aqueous solutions. So this is kind of specifically for water. When we try to dissolve compounds in water, what we see is what we call this idea of hydration. So the water molecules arrange themselves so that they are attracted to the ions. And remember, if something is polar, that it has a positive end and a negative end. Something we talked about way back when. But something being polar means it has a positive end and a negative end. And what we call hydration is the arrangement of water molecules around an ion. Whether that ion is positive or negative means the water will put its negative or positive part towards that part. Okay. And I do have a picture of this. What this means is, so our water molecules are our red and blue ones, and our lithium particles are our purple ones, and our green ones are our chloride molecules. Chlorine is negatively charged. Water has positively charged hydrogen atoms, which are the blue things on the water molecules. Those positively charged hydrogen atoms orient themselves towards the negatively charged chlorine and do the opposite on the positively charged lithium. So this is what we call hydration. It's just the formation of this like surrounded surface of our ions with water molecules. Depending on the size of the ion, so the chlorine or the lithium, that's how many water molecules will actually be determined to be around it. This is just kind of an idea of what's happening. Okay? Non-polar solvents, just like we said, are going to dissolve non-polar solvents. They're just going to kind of have this interaction with each other in that since they don't like polar things, they kind of interact with each other because they like to not be around polar things. It's kind of weird, but that's just how they do. It's what they do. All right, from there, we talk about liquids, solutes, and solvents. So if we're talking about two phases that are liquid, we know that oil and water don't mix. Oil is nonpolar, water is polar. So the same idea still applies here. If they're two polar substances, they will mix. If they are two nonpolar substances, they will mix. And when they do that, if they mix well, we call them miscible. If they do not mix well, we call them immiscible. That's it for liquid solutes and solvents. Then we talk about the effects of pressure on gases. So we've talked about how solids will dissolve in liquids. We've talked about how liquids will interact with liquids. Next thing we want to talk about is how are gases going to come into play here. So if we talk about a gas that is trying to be dissolved in a liquid, the pressure itself will not have huge effects if we're just talking about liquids or solids in liquid solvents, but pressure has a lot to do with our gases. We spent a whole chapter and a half on this. If we are establishing this equilibrium, so we know that as gas particles go in, solvent molecules are then also escaping, or solvent gas particles are also escaping from a solution. We call that equilibrium above our liquid, just an equilibrium between the two. Eventually, if we leave that equilibrium undisturbed, the solubility of the gas is going to be the same all the time, right? We won't change the temperature. We're not changing the pressure. We're just kind of keeping everything stable. What we're going to talk about is what happens when we disturb that equilibrium. So for instance, if we increase the pressure of the solute gas above the solution itself, our gas particles are going to have to collide with the liquid more often, and this means more gas is going to dissolve in the liquid. So we've increased the solubility. Doing the opposite does the opposite. So decreasing the pressure of the solute gas above the solution means that the gas has more space to run around, and more gas particles are going to escape the solution. So we're going to decrease the solubility. So increase pressure, increase solubility, decrease pressure, decrease solubility. From there, we can actually measure this solubility of a gas in a liquid using a law called Henry's law. And we will talk a little bit more about Henry's law later on, but for now, what we want to say is that the solubility of a gas in a liquid is directly proportional to pressure. So, as gas pressure goes up, solubility goes up. As gas pressure goes down, solubility goes down. This idea of effervescence down at the bottom of the slide is exactly what we saw when we did our Alka-Seltzer tablet in water, that rapid escape of gas, so that very intense bubble that happened, or that very intense bubbling feeling that happened that you saw really fast and could kind of catch you off guard if you didn't know it was coming, is called effervescence. The effects of temperature on solubility. So as we increase temperature, we're going to see that will decrease gas solubility. However, increasing temperature increases solid solubility in a liquid. So at higher temperatures, our equilibrium with gas is going to decrease the amount of gas that actually gets dissolved. Now, there's a number of reasons for this. Equilibrium is going to be reached with fewer gas molecules. There's a couple of different reasons why this happens. Gases are generally less soluble if there's fewer gas molecules in solution. This has a lot to do with kinetic energy. As we increase temperature, we see kinetic energy is going to go up, and the higher the kinetic energy, the harder it is to actually keep gas molecules in one place. Same with any molecule, right? At higher temperatures, we actually get liquid molecules starting to try to become gases. So this generally decreases our gas solubility because the gases want to escape and they want to be free and they want to run around. Increasing temperature also generally does the opposite with solids and liquids, as we talked about before. And this was where we talked about our supersaturated solutions. So the solubility of some are going to get very, very high because we've increased temperature. Temperature increases the rate at which things are moving. The faster they move, the more likely they are to collide. The faster they collide, the more likely they are to dissolve or change phase, and et cetera, et cetera. There are some exceptions to that rule. They're not very many, but there are some exceptions to this rule. Okay. And what we can see is we can actually look at our next graph of the chapter, which is going to have solubility. Remember that solubility is going to be reported in terms of the amount that gets dissolved of the solute in 100 grams of water. That's on our y-axis versus temperature. So as we change the temperature of some stuff, we see solubility go up. And for the most part, a lot of things are going to increase as we increase temperature, because we're looking at those solvent-solute interactions. We're seeing the particles move faster particles, more collisions, and so on and so forth. But there are a few exceptions to this, and there are some reasons that have been proposed why. For now, we're not going to get into that. Our last lecture question of this section, for section 2, is to tell me how you can increase the solubility in any of our phases. So I want you to talk about all of the phases. How do you increase the solubility of a liquid in a liquid? How do you increase the solubility of a gas in a liquid? And what are some of the ones that we discussed? And we did discuss 3 just now, so go back and look and get those written out. Remember that these are getting emailed to me when you finish. That is almost the end of section 2. We have one more topic. We're just going to introduce enthalpies of solution, and then we're going to stop. So enthalpies of solution, enthalpy is a form of heat or energy change. Enthalpies of solution are going to involve how much energy is it required to do something to a specific solute. So the formation of a solution has an amount of energy required. That amount of energy required is typically referred to as the enthalpy of a solution. Now, once something is in a new phase, so once we take our solid and we dissolve it into a new phase, we've broken apart the molecules and we've created either an electrolyte or a non-electrolyte solution, whatever is happening has an energy associated with it. And that energy is going to be referred to as an enthalpy of solution. Now, remember, just to kind of rehash, all of this is talking about how solute particles are going to form what we call solvated radiuses. So solvated is another term for hydrated. Except that with hydrated, what we're saying is those are surrounded by water molecules. Solvated is a more general term that says a solute particle is now surrounded by solvent molecules. That solvent molecule can be anything. It doesn't have to be water. And just to kind of give you an example of the next thing we're going to talk about is just kind of, here's this graph at the bottom of the screen, and it talks about the energy that takes place over the different steps of the dissolving process. So in step 1, what we are doing is we are going from solid particles becoming separated from the solid. So we take a solid chunk of something, we toss it in our solvent, and we are tracking how much energy it's going to take or absorb to go from the solid phase into the liquid phase. In step 2, our solvent particles are still being moved apart, so this is still happening. We're still seeing the solid become more of the liquid and as much as it possibly can. And then in step 3, if we kind of reverse the process, we will see that solvent molecules are going to be releasing energy when they are solvated solvent particles are attracted to our solid particles, and they're solvating those solute particles. And when that happens, our solvent is actually releasing energy to do it. Now, the sum of the energies that are required for the solid to give up its particles and for those solid particles, those solvent particles, to get moved apart from the solid, that's going to be energy that has to be put in. The energy released when the solvent actually surrounds the particles is referred to as the energy released. Obviously, the sum of all 3 of these steps is the enthalpy of the overall solution. So this is the enthalpy, the energy required to actually do the process of creating a solution. And that's it for section 2. We will come back in section 3 next week.